This proof requires knowing uniform CDF is identity. To show that, let big Z be the CDF of big X. Assume the CDF of X is continuous and increasing. Given Z is a CDF, it takes on values on the closed interval 0 to 1. We start off with the CDF of Z, which by definition is a probability that big Z is less than or equal to our dummy variable little x. Next, big Z is equal to CDF of X. We apply non-decreasing F inverse to both sides. We see that CDF of X is the probability of big X less than or equal to some random variable. A function composed of its inverse is the identity, so we are left with our dummy variable little x. Let F be an invertible CDF, so any real number maps to the open interval 0 to 1. We say a mapping is invertible if there exists a bijective 1-to-1 path. If big U follows uniform 0 to 1, then F inverse of big U follows F, that is, F inverse U has CDF F. Proof: let x, y be real numbers and a, b belong to open interval 0 to 1. If x is not greater than y, then f of x is not greater than f of y, since a CDF is not decreasing. From assumption of f is invertible, we have 1 to 1. For the same reason, if x is strictly less than y, then f of x must be strictly less than y. If x is not equal to y, then f of x cannot equal to f of y from 1 to 1. To prove an if-then statement, we show that if hypothesis P, then not conclusion Q is always contradiction. If negated conclusion is always wrong given a hypothesis, then unnegated conclusion is always correct. We can show that if A is less than B, F inverse of A is less than F inverse of B. For the sake of contradiction, we negate this statement and assume F inverse A is greater than F inverse B. We apply F to both sides and see that A is greater than B, which is a contradiction, so negating the contradictory statement must be true. F inverse is less than or equal to X if and only if A is less than or equal to F of X. We get the forward statement by taking F of both sides. We get the converse statement by taking non-decreasing F inverse of both sides. What does this equation mean? F inverse of A less than or equal to X if and only if A is less than or equal to F of X. Earlier, we defined A as some output of our CDF. F inverse A maps output back to our input. If X is our CDF input, F of X is our CDF output. If our pink value is less than yellow value on one axis, then it is necessary and sufficient to say pink value must be less than our yellow value on the other axis as well. Now I want to show you that the CDF of F inverse of A is the uniform CDF. If two random variables have the same CDF, it means that they have the same probability distribution. We first start with CDF F inverse U less than or equal to dummy variable X. We apply our bijective property to get probability of big U less than or equal to F of X. We now have CDF of U evaluated at F of X. We rewrite our uniform CDF as H, so we can see that after applying identity, we have F of X. We can also invert discrete CDFs. The pseudo-inverse is defined as the infimum of the greatest lower bound. The minimum of a function belongs to the range of the function and is also the infimum, but the converse is not necessarily true. The infimum is the lower bound of a function. When the set of numbers is finite, the infimum is the same as the minimum. When the set of numbers is empty, any number is the lower bound, so the infimum of an empty set is plus infinity. We must then show that the set is not empty. Afterwards, we will be left with a finite, non-empty set, so infimum is the minimum.